Hello and welcome. We'll be doing the transition metals today. So as requested, I'll jump ahead a bit in the syllabus. I'll fill in the others in a bit of time. Now this topic overlaps quite a lot with the inorganic one, which follows it as well. So you do need to be able to link together both of these topics quite effectively for questions in exams. But I'll work through it sort of as it appears in the syllabus for what you need to be able to know and do. So first off, what is a transition metal? So as you can see up here, it's where we've got a stable ion which has got a partially filled D subshell. So make sure you get that in there. I've seen people lose marks where they've just said a D shell. No, your shells are your first, second, third energy level. You're talking about a D subshell here. So the transition metals aren't actually everything in the D block. It's only titanium to copper, which are transition metals. So even along that period, things like the scandium, the zinc, they are not. Because if you write out the electronic configuration for these two, you will notice they've either got an empty D subshell or a full D subshell. So they don't classify as transition metals. So they will not show the characteristic properties which the other guys in here do. Now there are 5 main things which we are going to look at with transition metals. Exams tend to just classify 4 of them. They don't really treat shapes as one of them, but I'll go through what shapes there are. So if you're shown 2 or 3 of these and asked to name another one, the 4 which they are looking for are the complex formation, colour, variable oxidation state and the ability to act as a catalyst there. So first off, complex formation. Right, so as we can see here, this is generally what it looks like. So this is a complex here. So what's happened is we've got a central metal ion and it's surrounded by ligands. Now what ligands are? They are electron pair donors. So again, electron pairs, make sure you get that in. And as you can see here, it's not normally shown this way, but I've shown it just for clarity. It's a dative covalent bond or a coordinate bond, whatever you wish to call it. So for an example, we need an electron pair on our species. So these are called unidentate ligands. So the uni just means one, so they bite with one, and the dentate, it's where we get the word dentures from, just means teeth. So they bite on with sort of one link. So we'll come on to the bi and polys in a second. So for something to be able to act as a ligand, it must have a lone pair of electrons. So in the exam, if you're shown something like hydrogen and asked why can this not act as a ligand, well, H2 doesn't have a lone pair of electrons. So your common unidentate ones are things like water, ammonia, so you would have the oxygen and obviously the hydrogen's coming off the oxygen, but it would be the oxygen specifically which is attaching to the metal because the lone pair of electrons are on this. Ditto, it would be the nitrogen attaching to the metal in the middle there as well. So that's an octahedral shape. We can get other shapes which we'll come on to in a second. You can get the tetrahedral, square planars, things like that. Now a bidentate, this is where obviously we've got 2 teeth, so I've shown it shorthand here, the diamine, this just gets shortened to En at times. Then as you can see, it's sort of linking on in 2 places to the actual metal. So I've got 3 of these surrounding it because each of them is bidentate, so it's filling up the 6 links there around the metal. Now something just to tie into is what coordination number is. Now, coordination number is not the amount of ligands attached to the metal. So I'll repeat that, it is not the amount of ligands. What it is the amount of bonds formed to the metal. So going back to this one, you can see we've got 6 unidentate ligands there attached. So there is actually 6 dative covalent bonds to that metal. Now across here we've only got 3 ligands, but with them being bidentate there is still 6 bonds there. So this one still has a coordination number of 6, just like this one across here. Now with the bidentates at times, sometimes you don't see them in the shape like this. You could have sort of a bidentate there and a bidentate around here. and then two unidentate ligands at sort of opposite ends to each other. So I've seen that in exams where you've got two of the diweights here, the ethane diweight, attached around the sides, and then water at the top, water at the bottom, and it asks you to state the angle between them. Well, you can see here it's still an octahedral shape, so the angle between the waters, if there was one up here and one down here, would be 180 degrees. And obviously all the angles in here, 90 degrees. So this links right the way back to your Chem 1 shapes with remembering the angles there. So these are your two common examples of the bidentate ligands, by the way. So as you can see down here, this isn't the actual structure, there is actually resonance taking place between these. So sometimes you'll just see this shortened to C2O4, 2- as well. But simplification, that's what you could draw it as well. So these here with the lone pairs on the oxygens, they would be what links to the actual metal again, dative covalent bonds. Now your polydentate, the big example, what you always see for this is EDTA. So this structure tends to just get shortened to this. So obviously it's a bit of a hassle drawing this. Now for where the actual so this is a hexadentate, by the way. The poly just means many, but specifically you should be able to draw the six, well, show where the 6 links come from on this. So 1, 2, 3, 4, 5, 6. So the 2 nitrogens here, they've still got a lone pair of electrons, because obviously the 3 bonds, lone pair, just the same as across here with the ammonia. Then you can form a dative covalent link there, dative here, 3, 4, 5 and 6. Now the reactions which they tend to show with the EDTA are why, say, if you've got a metal ion in a complex formation with 6 waters around it, why EDTA would be very good at kicking off all of them and just linking and surrounding the metal, linking up with all 6 of its teeth there. And that ties in with entropy. So if you're starting with 2 moles of species, so this and this, then what you would get is when your EDTA joins onto the metal, all 6 waters would be displaced. So you'd end up going from 2 species up to 7. So 2 moles to 7 moles, that's a big increase in entropy. So entropy really favours the disorder which is produced by that reaction. But I'll recap that in a second because, again, that overlaps a bit with the next topic. Right, so now on to shapes. Right, now looking at the shapes. If you're wondering about the charges, by the way, I am just using a generic 2+ metal ion for each of these. You can obviously have 3+, so forth. Right, so now your most common shape that you'll probably see is your octahedral one across here. So as you can see, 180 degrees between each of these, and then we've got sort of a square around the middle, so 90 degrees, so forth. So exactly the same, as I said, as your Chem 1 shapes. So it tends to be the small ligands which adopt that shape, so things like water, ammonia, obviously your bidentate ligands as well will tend to adopt that shape because they're going to be using twice as much space so they can still fit in nice and effectively. Now your bigger ligands, so things like the chloride here, because they're big and fat, they cannot really fit 6 in around the metal. So these are clumpy, taking up lots of space. So it tends to adopt the tetrahedral shape, as you can see there. So each of the chlorides coming in, hence why the overall charge here is 2-. You can get the square planar as well, but the square planar is less common than the tetrahedral. The reason why is obviously square planars are not using the maximum amount of space. So you've got a lot of space above this platinum and a lot of space behind it. So these guys could space out a bit more. Now this is cisplatin, so it's probably a most common square planar compound that you'll actually see. We'll come on to looking at it in a bit with terms of its anti-cancer properties and what it's used for with that. But you can adopt either the tetrahedral or square planar shape. Now so again, remember your angles, 109.5 between all of these and obviously 90 degrees between all of these there. And the most common linear one which you'll see is this up here, Tollens reagent, so the ammonical silver there. And obviously 180 degrees between each of these, nice and easy, so just straight flat linear compound. So that's your four basic shapes which you need to know for the transition metals there. So on to the third part. One little thing before we do, something just to mention with the shapes, is when you've got a compound like this, by the way, you can sometimes have a counter ion attached to it. So as you can see here, we've got a 2+ charge. So this compound could quite likely attract a sulfate ion to float around with it. So a sulfate ion, so obviously you should know that, SO4 2-. This could be attracted to that and float around with it. It does not affect the shape. So say if you see something like FeH2O6.SO4, then this is a counter ion. It's purely just attracted ionically because of the opposite charges there, so the electrostatic attraction, but it's not dative covalently bonded to the actual metal like these guys are, so it doesn't actually affect the shape. So the shape of this, even if it had this floating around with it, would still be octahedral in there. Okay, so on to the third part, colour. So the transition metals, they all show colour, and the reason why, as we'll come to look at, is to do with the actual D subshell here. Now I've put on the left hand side there 3 key words, so absorb, promote and reflect. Make sure every exam question when you're asked about colour to try and get those in. So we'll talk through sort of the full sentence rounder, but those are your 3 keywords. Make sure you get them highlighted in any notes. Now initially, as you've probably been used to, your 5D subshells are all of the same energy. That's true when your metal ion is isolated, so when it's by itself. However, because of the shape it adopts, when any incoming ligands come in and start joining onto it, some of the subshells end up getting higher energy, some of them drop a bit. The ins and outs of it, sort of degree level chemistry, which you might go on to. So as you can see, some of them increase in energy, some of them decrease in energy, but overall the average of them still levels out as the isolated there. Now, as you can see, I've just put increases 3/5, decreases 2/5. It tells you nothing so far about how big or small that actual change is. So it's mainly the ligand which will be doing that. Some of them only split it a little bit in terms of energy. Some of them will split it quite a lot. Now, as you can see here, I've got this equation as well. It's useful knowing what these terms are. So E stands for energy. H is Planck's constant, so if you do physics, you've probably used that by now. It's a really, really small number, 6.626 times 10 to the minus 34. In simple terms, for those who don't do physics, it's just a proportionality constant linking together energy here with the frequency of the light which we're going to be looking at. So where the actual colour comes from. So initially we've got our metal here, it's got some ligands coming in, and what will happen is it will absorb light. So that's your first bit there, you absorb light. Now the second bit is promote. So light in effect carries energy, so depending on the frequency of light, if it's say red and it's just got a very low frequency, so think of sort of a C on a calm day, that will be red, so nice shallow waves. Whereas if it's got a high frequency, when it's like this, that's blue. So blue's got the high energy, red's got the low energy. So depending on how much this is being split will tell you how much energy is needed to actually promote an electron from the lower energy here up to the higher energy. So if it's just a small split, then you only need small energy, so you would absorb red. So the red would be absorbed to promote the small distance. Whereas if you had a ligand which had split them a large amount, then you would need a large amount of energy. So the large amount of energy comes from blue. So you would absorb the blue there to jump from being right the way down here to promote your electron right the way up to the high energy there. So once you've actually promoted that electron, every other part of the light is reflected. So what you will actually see, so using a colour wheel like this, you don't need to remember that, by the way, heck I don't. Then say if we absorbed the actual red, what you would see would be the cyan here, effectively teal, being reflected back at you. Whereas if your splitting was a little bit greater and you needed more energy to promote the electron, then you would absorb the yellow there to promote it, and it would be the darker blue here which would be reflected back. So as you can see, as the splitting increases, then the colour that we absorb goes round here, and what you see would be the opposite to it. So if there was a massive degree of splitting and we needed a lot of energy, then we would absorb the blue here and you would see the yellow being reflected back. Now that's a little bit of a simplification because that's assuming we're only absorbing one specific little bit of energy. You can absorb across multiple wavelengths and then it gets a bit mucky. But in terms of the AQA level syllabus, it keeps it a bit more clear cut. So getting those three key things, so you absorb light to promote the electron here in the D subshell, and then what's reflected is what you actually see coming back at you. Now what changes colour? So the oxidation state, so say if we've got a metal which goes from being 2+ to 3+ because it's been oxidised by air, something like that, and it's had an electron ripped from it, then that will change the colour. Ligands, now the ligands are the big ones, so if you say change from water to the chloride, or if you went from chloride ion to a cyanide ion, then altering the ligands like that, they will change the colour big time. So an example is, say if we went, when we will be looking at the copper chemistry, then going from water and changing it to the ammonia, then you'll see sort of going from the light blue to the dark blue with that. And it's to do with the amount of splitting which the ligand imposes on here. And the final bit there, the coordination number. So sometimes the ligand and coordination number go a little bit hand in hand. It's hard to tell who's what's actually doing the change, because if you change the ligand, then you might also change the actual shape. So say if we booted off 6 waters and replaced them with 4 chloride ions, then the oxidation state would be the same, but we've changed the ligand and we've changed the coordination number. But again, the ins and outs, the muckiness like that, tend to just get bypassed at this level. Now questions sort of which get asked about this, sort of why don't the aluminium complexes show any colour? Well, aluminium, it's not a transition metal. So if we don't have any electrons in this D subshell, or if the D subshell is packed there, if we've got all of these full, so we've got 10 electrons in there, then either A, we've got no electrons to promote, or B, there is no space to promote an electron to. So they wouldn't show colour if either A, they've got no electrons, or B, it's full. Now, colorimetry we'll come on to as well. I'll show you how to sort of plot a graph there and use colour to determine concentration. Okay, so you can use a UV vis spectrometer to do colorimetry, and the reason to do it is mainly because it's just rapid, it's dirt easy. You just pour in a little bit of your sample and stick it in the actual machine, and that's pretty much it. So it uses the Beer-Lambert law, which sort of relates the actual concentration to the light which would be absorbed. So what you would do is you would set up a some known standards. So you'd get obviously there your concentrations 1, 2, 3, 4, 5 molar. You'd stick them through the machine. You record the absorbance of those, and then when you've got your unknown sample, so the one which it tends to be used for in this syllabus is the manganate reactions. The reason why is obviously got a nice dark purple colour, so you can check the concentration for sort of how deep that purple is and affect to relate it to it. and obviously it doesn't interfere with any of the reactions, basically because all you're doing is just passing light through it. It's not like NMR or mass spec where sort of you've got to use other chemicals in there, or mass spec actually bombarding up your species. So once you've actually put it through, then as you can see, your unknown would just give you an absorbance from the machine. You simply just read it across on the graph, go down, and it would tell you your concentration there. So a very quick, very easy piece of analytical chemistry to do, and that's what colorimetry is useful for. Okay, so the variable oxidation states. You've seen these when you've been doing all the redox reactions in the past, and it's more or less just a continuation of that. So as you can see up the top here, we can see the 2+, and obviously each oxygen more electronegative, so -2 for each of them. Overall charge 0, so the manganese must be +4, and ditto 4 times -2 -8. We need to get up to -1, so the manganese must be +7 there. So the transition metals, their oxidation state can change, and it's what gives them the ability to show colour, the ability to act as catalysts, things like that. So this is sort of the topic which allows them to show the other properties. Now I've got a working out here for the June 10 question 7D. So if you want to pull that up on the computer or print it out and have it beside you, then we'll talk through how it's actually done. Because the variable oxidation states, usually they're just going to be getting you to be able to work out the half equations there, link them together into a full equation, and then do a titration calculation using them. So it's quite a long question. I imagine a few people probably just wet themselves in the exam when it appeared, but it's a nice big 6-mark question. If you can run through it in a couple of minutes, then it's a few minutes that you've got to spend elsewhere. Okay, so the first thing, it asks you to calculate the percentage of the iron 2 ions which have been oxidized by air. So the full question, what's happened is you've got some iron sulfate, you've chucked it into water, you've let it dissolve, and the cap's been left off. Some of the iron 2's been oxidized to iron 3 by air, and then what you've done is you've taken a sample of the remaining solution and you've basically checked to see how much iron 2's left by reacting it with the dichromate. So the dichromate, as we can see here, is acting as an oxidizing agent. It's making the iron 2 lose the electrons to turn into iron 3+, and in effect this is being reduced. So reducing agent, oxidizing agent. So the dichromate's just checking to see how much iron 2+ is left. So the first thing I did originally was I checked to see how much iron 2 was present in the initial sample. So the way I've done this is I know the total MMR, it tells me, the MR is 277.9. Now I know iron's 55.8, hopefully I just use my memory for that rather than getting the periodic table out. So roughly a fifth of that overall compound is iron. So roughly a fifth of the mass will be the iron 2+. So what I've done there is effectively the MR of the iron divided by the MR of the complex, and then times by 10, since I was told the overall mass was 10 grams initially. So that comes out as 2.01 grams, well roughly 2.01 grams of iron 2 was originally present in the sample. Now the next thing what I did is I did some half equations to get me a ratio between the iron 2+ and the dichromate for how they're going to react together. So the iron 2+ we are told is oxidized to iron 3+, so it loses a single electron as we can see here. So very easy half equation there. Now the dichromate and the manganate half equations, I wouldn't say to try and remember them off by heart because obviously they're quite big, but you should be able to quickly knock them up on the spot. Now iron 2+, it causes the chromium to be reduced to chromium 3+. So Zinc we'll look at in a bit can cause it to change to the 2 plus as well, but the iron just causes it to go to the 3 plus state. So that's probably the one thing what you need to remember. So the first thing what I did was I balanced the chromium. So I've got 2 chromiums here, so I made it to have 2 chromiums there. The second thing, I looked at the oxidation numbers. So the oxidation number of this would be 3 plus. Across here, this is plus 6. The reason why, 7 times the minus 2 for the oxygen, minus 14. I need to get up to minus 2, so I need 12. That 12 is shared out amongst the 2 chromiums, so each of them are plus 6. So each chromium is going from plus 6 to plus 3. So each of them needs 3 electrons. So I need 6 electrons in total because there is 2 of them. So that's where the 6 electrons comes from. Now you were told it was in a dilute sulfuric acid solution. So this is why we're using H plus here. So I need to make the overall charges the same. So we've got 8 minus here, we've got plus 6 here because 2 lots of plus 3. So to get from minus 8 to plus 6, I need 14 hydrogen ions there. And then just to balance it off, 7 waters across here. So as you can see, if I wanted to combine these equations to get me a full balanced equation, I would need to multiply this line by 6 to make the electrons the same. Hence, I'm going to have a 1 to 6 ratio reacting between these. Okay, so now back onto the math. So I need to work out the moles of the dichromate which actually reacted. So that's very easy. It's just as you've done in the past, AIDS concentration times volume. Remember to convert to decimeters cubed. And this tells me the moles of the dichromate used. So now I need to work out the moles of the iron 2 plus. So I've multiplied by 6 because it's a 1 to 6 ratio. So each one of these will react with 6 of these. Hence the multiplication by 6. So that would have told me the moles of iron 2 plus present in 25 cubic centimeters. So read the question very carefully. You did not use all 250. You took a 25 cubic centimeter sample. So this is why I've multiplied by the 10 here. Because just multiplying by the 6 tells me the moles in 25 cubic centimeters. Multiplying by the 10 now tells me the moles of iron 2 plus in the 250 cubic centimeters. Then onto the end here, I've multiplied again by the MR of iron. So this tells me 0.793 grams were left. Now read the question very carefully. It asks you to calculate the percentage that had been oxidized, not the percentage left. So this was the mass we started with. This was the mass left. So therefore this, subtract this, tells me that 1.217 grams was oxidized. So now I just look at doing a percentage calculation. So the percentage the mass oxidized divided by the mass originally times by 100 to convert to a percentage, and that tells me there the percentage of the iron 2 plus which was oxidized to the 3 plus. One thing to note just with these reactions, it ties in a bit with the electrochemistry sometimes, what it gets looked at. The reason you're using the dilute sulfuric acid is if you were using the concentrated, it would compete with the dichromate, and that the concentrated sulfuric acid would also cause the iron 2 plus to lose electrons. So you wouldn't get an accurate reading for how much dichromate was actually used up. Likewise, if you had, say, concentrated HCl in there, then the dichromate is more powerful than the chloride ions, and what it would actually do is it would rip electrons from the chloride ions as well, so you'd end up with going from Cl minus to Cl2. So you'd think that there would be more iron 2 plus present than there actually was, because some of the chloride would be providing the electrons. With something like ethanoic acid or weak acid, then that wouldn't provide enough hydrogen ions here, because obviously it only partially dissociates, so it doesn't give off enough compared to the dilute sulfuric. And similar with using nitric acid as well. If you're using concentrated there, then just the same as the concentrated sulfuric, that would cause the iron 2 plus to turn into iron 3 plus as well. So you'd end up using less of this, and you'd think there wasn't as much iron 2 plus. So that's just why you use dilute sulfuric in these reactions. Okay, so what I've shown you now is sort of the exam favourites for being able to do these titration calculations. So you should be familiar with them, although you're usually given the reactant and product oxidation states. Then, as you can see, the iron goes from iron 2 plus to iron 3 plus. We've got the manganate reaction here, so it's usually something like potassium manganate, and it goes to the Mn2 plus. You do need to be able to recognise the colours as well and being able to state what you'd actually see. So the purple, very dark purple solution, so this titration is self-indicating. In effect, as soon as you see the purple disappear and it becomes colourless, you know it's completed. The iron, it causes the dichromate to be reduced to the green 3 plus stage here, so the chromium 3 plus. So the difference between the iron and the zinc is that the zinc is better at reducing the chromium, so it can turn the chromium from the 3 plus into the actual 2 plus. So what you'd see is sort of multiple colour changes in this. You'd see it go from orange to green and then green to blue as it continues to take in electrons from the actual zinc. So be aware of the difference between the iron and the zinc with that. Now what I've done is obviously I've underlined, say, the dichromate here going to the 3 plus and obviously the manganate to the Mn2 plus. Practice writing the half equations for those so that you can quickly stick them together and get the ratio for the reactants here for doing the titration calculations. As I said, it's probably easier doing it that way than trying to remember all 4 of these off by heart. Okay, so I'm skipping on to looking at chromium now rather than the cobalt. The cobalt, there's a few of them to look at, so I'll just get this one out of the way. So the syllabus wants you to look at the oxidation of the chromium 3 plus by hydrogen peroxide. So as you can see, yeah, the hydrogen peroxide, it's being reduced, it's gaining the electrons, and it's acting as an oxidizing agent, causing the chromium to lose electrons across here. So we're going from the chromium 3 plus, because obviously the hydroxide ion, each of them negatively charged. So if you've got 6 of them giving you 3 minus, then we must be plus 3 here. And we are going to the chromate. Now these are under alkaline conditions. The way to do the half equations under alkaline conditions isn't really that much different to the acidic. Just rather than using H plus here, as you can see, we're just going to use OH minus instead. So if you can do the acid ones, not really that much of a hassle getting these done. So initially up here, as you can see, we've got the chromium hydrated. We're using excess of sodium hydroxide, anything like that, to get it into the state across here. The reason why is if we want to take electrons from it, it's very hard to take electrons from things that are positively charged. It's obviously attraction between them, but keeping a hold of them much better. Whereas when you've got it negatively charged, it's a bit easier to remove the electrons. So that's why this is done up here first. Now talking you through the half equations first. So my chromiums were balanced initially, so that was fine. So I went on to look at the oxidation state. So I'm going from plus 3 to plus 6. So I must be losing 3 electrons. So hence 3 electrons added on this side. Now I need to balance the charge with hydroxide ions. So my overall charge here, minus 5. So for there would be minus 3. So that's why I needed 2 hydroxide ions to make each side minus 5. Finally, use water to balance it. So if we look here, we've got 6, 7, 8 hydrogens. So I needed 4 waters there to balance it. Now the hydrogen peroxide half equation, nice and easy there. As you can see, H2O2 goes to 2OH minus. And if I look at the oxidation state, -1 for the oxygen here, -2 here. So each oxygen is gaining 1 electron, so I needed to gain 2 electrons in total. Now if I combine them together into a full equation, obviously the electrons need to cancel, so I multiplied this line by 2 and this line by 3, and then just a case of cancelling whatever appears on each side. So some of the hydroxides cancelled each other out, which is why I've just got 2 left here and none of the reactants. So there's my overall equation showing how the chromium complex across here is being oxidized by the hydrogen peroxide, and it's giving me the chromate. So again, remember your colours with these. Green, we're going to the yellow here for the chromate. Okay, so to finish it off with the variable oxidation state, it's going to look at cobalt, so it's changing from its 2+ form to the 3+. So again, up here we can just see we've used ammonia to get it into this state, and then the reaction with the hydrogen peroxide, as you can see here, the hydrogen peroxide is oxidizing it, causing it to lose electron, whereas the hydrogen peroxide is being reduced, so it's gaining them. I went through the same stages as before for balancing these, so looking at the oxidation state, so the 2+ to the 3+, so I needed an electron on this side, using the OH minus to balance it, so -1 this side, it was neutral before, so I needed 1 OH minus there to give me the same charge, and then H2O just to balance it. So you should be able to stick these two together, no problem at all. You need to do is multiply this line by 2 to make the electrons the same. So your hydroxides would cancel each other out, and then that would be it. Now looking at the oxidation via air, so O2 here. Now I've seen it sort of either using this compound, going to obviously the 3 hydroxides attached instead, or when you've got 3 of the ethylene diamine attached to it, so the NH2, CH2, CH2, NH2, and just going from the cobalt with the 3 of those, and the cobalt's got a 2+ charge, to the cobalt, still got the 3 of the ethylene diamine attached to a 3+. That equation would be very easy. All you would need is just the 1 electron being lost across here. And then as we can see here, now I've shown these separate just so you can see how I've actually worked it out. So first off, I started with O2. It goes to the 2 hydroxide ions. Now in order to do that, we're going from 0 to -2 for each of the oxygen. So each oxygen needs 2 electrons. So that's why I've got +4 electrons on this side. Now then I needed to balance the charges with the hydroxide. So currently I was -2 with -4. So this is where the extra 2 hydroxides came from. So you can just have it written as 4OH minus. I just showed it separately there just so you can see how I've actually worked it out step by step. And then as you can see, just balanced it off with water across that side. So to combine these, multiply this line by 4, leave this line as it is. These would obviously cancel each other out. You'd lose your 2 waters there, you'd be left with 2 on this side, and then you'd be able to stick them together from that. Now hopefully with looking at all these reactions, you're probably thinking that's too many to remember. Good, I wouldn't try and remember all of these off by heart. Get used to actually just being able to work out the equations for these, taking sensible guesses, making sure things are just balanced is the most important thing. If you look at plenty of exam questions, the example what I was just using there with the ethylene diamine, there are multiple ways which that reaction can actually be balanced, and as long as you put a correct one, then it's perfectly fine. So it doesn't have to be a specific one, just any correct balanced equation showing it, going from the cobalt 2+ to the cobalt 3+, and that's perfectly fine. So again, just practice getting your half equations done. Okay, so final little bit then, looking at catalysis. So catalysts, just the same as you've been aware in every part of chemistry coming up to this, provide an alternative pathway for the reaction to take place with a lower activation energy. So you'll get your products quicker, more money, everybody's happy. So you've got two types. You've got homolytic and heterolytic. So the homo means in the same phase, whereas the hetero, different phase. Now the fact that the transition metals can act as catalysts, it's due to the variable oxidation state. We'll point that out when we look at the contact in a second. It's the easiest one to see with it. Now it goes through a few different stages when it's happening there. Adsorption, and then the bonds weaken, the reaction happens, and desorption. Now it's ad rather than ab. So the difference between them is absorption sort of gets chemically taken in, whereas adsorption, it just sits on the actual surface of the metal. So you've got your chemicals floating about, you've got your metal, it'll usually be in a honeycomb structure supported on something just to increase the surface area, again increases the rate even more. And the chemicals which are reacting will come near it, they'll form weak bonds with the transition metal. Now the fact that they are forming bonds means, say, the bonds between them, if we're looking at the Haber process, the strong triple bond between the nitrogen, that would become a bit weaker. So what it allows to happen is that bond to actually break open and the hydrogens instead to start sticking on the nitrogen. So the bonds weaken and then the reaction happens, and then after that, once you've got your ammonia, it desorbs off the actual surface. Now you do need to be careful with the choice of your actual metal. So if we use tungsten for an example, tungsten bonds very strongly with things. So when that nitrogen and hydrogen come along, then they will form a strong bond with the tungsten and they'll just sit there. So you won't actually get any ammonia being given off as the product. Even if the ammonia did form, it would be bonded so strongly with it that you wouldn't really see it leaving in any case. Silver. Now silver, sort of, it's like a three bears story this. So too strong, silver is too weak. So you've got your nitrogen and hydrogen floating about, silver just doesn't even attract them at all. So if it's not attracting them, it's not weakening the bonds, it's practically useless as a catalyst, it's not doing its job. Whereas platinum and nickel, then those are your just right ones. So they adsorb the actual materials, they weaken the bonds, and then they release them afterwards. So there's three sort of main reactions which you need to be aware of for this. You've got everybody's favourite, the Haber there, so iron acting as your catalyst. You can use things like platinum as well, just they're more expensive, so you just chuck in some dirt cheap iron instead. Now the contact one, so this is where you're using vanadium oxide, as you can see here. Now you can see the oxidation state changing quite clearly in this. So we are going from +5 here to +4 across here, and then we are going from +4 back to +5. So the overall start and end hasn't actually changed, it's only flicked about in the middle, but the catalyst, it's reformed back to itself at the end, so that's why it's classified as a catalyst. So if you wrote the full overall equation for that, then this would cancel, this would cancel, so all you're left with is the sulfur dioxide reacting with some oxygen, get you some SO3 across here. Your other ones are using methanol, to get methanol across here, so we're reacting the carbon monoxide with some hydrogen in the presence of Cr2O3. Now catalysts can be poisons, it's just the same as biological catalysts can be killed by raising the temperature. Then there are certain chemicals here which can poison your catalyst. So what actually happens is just the surface, it's covered, so you lose your active site. So these chemicals bond so strongly to the metal that they in effect just fill up all the space, cover the surface, and therefore your actual reactants can't adsorb onto it. So sulfur, for an example, in the Haber process, so the sulfur bonds strongly to the iron, and lead in catalytic converters, which is why fuels are unleaded. So if you want to make sure that your catalyst doesn't get poisoned and go and meet its maker, then just make sure you purify your actual reactants, what you're putting in. So make sure your petrol doesn't have lead in it, and likewise make sure there's no sulfur impurities when you're pumping through the nitrogen and hydrogen. Okay, so for the homogeneous catalyst, this is probably the main one what you'll actually see here. And what it looks at is effectively, because we've got two negative charges there, then there's going to be repulsion between them. So a lot of these, if it talks about why a reaction's slow, things like that, just get across the point that it's a very high activation energy. So more slow reactions, just because it requires so much energy to put in that it barely proceeds at all. So what you can do is you can use either iron 2 plus or iron 3 plus as a catalyst in this. It doesn't matter which, because I could have quite easily wrote these equations the other way around and it would have made no difference. So it could have been that the iodide turns the 3 plus into the 2 plus, and then the 2 plus gets turned back into the 3 plus in this reaction. So either way is perfectly fine, because people tend to think that it has to be done this way because it's usually the way that they see it written. No. Right, and so the iron here is acting as a catalyst, again just provides an alternative pathway with a low activation energy. Effectively what it's doing is just acting as a middleman here. As you can see, the oxidation state is changing, going from the 2 plus to the 3 plus, and the 3 plus back to the 2 plus. So the reason why it's acting as a catalyst here is because of that, and also the attraction between the positive and the negative ion there, then that's why you're going to have a lower activation energy, because there's going to be attraction there rather than repulsion. So what we'll look at next is an autocatalyst reaction. Okay, so we're looking at an example of autocatalysis now. So this is where one of your products actually acts as a catalyst. So in this reaction here, this is the exam favourite. As you can see here, same as before, we've got two negative charges. So these are going to be repelling each other. So very slow reaction, very high activation energy there. So we need something to help speed it up. Now, initially we're going to have no Mn2+. So if we were to plot a graph of the concentration of the manganate here against time, as you can see, initially the slope's going to be very shallow because the repulsion here, very slow reaction taking place. But as some of the Mn2+ is produced, and as you can see here, we're going to have two reactions taking place, where the Mn2+ is reacting with the manganate, turning to Mn3+, and then it's reacting with the diaweight there and going back to the Mn2+. So in doing that, we're going to have attraction, same positive negative attracting each other. So as you can see here, it's going to be going nice and fast to this part, nice and steep. So this is where we've got some actual catalyst there. It'll slow down towards the end, just basically because your reactant starts to run out. Now you can do a colorimetry analytical technique to sort of measure the concentration of this as time's actually going along. Reason why is obviously manganate, MnO4-, has got a nice deep purple colour, whereas your Mn2+ and so forth, everything else in there doesn't really exhibit much in the way of colour. Most of them are colourless. So when you put it through the UV vis, it'll just be the concentration of this which you're actually detecting. So that's how you can sort of plot a slope like that. So, because if you looked at it with your eye, all that you'd be able to tell is just that you're starting off with a deep purple colour, and then as soon as you get to this part, it'll just pretty much flick straight away to colourless, because this will be that fast. Okie dokie, final little bit then, some other uses of the transition metals. So iron in hemoglobin up there, so the iron's oxidation state can flick about. That's why it's useful for carrying oxygen around your bloodstream. Obviously you need the oxygen to get to your brain, otherwise about 15 seconds and you die. So one of the problems with that, do not breathe in carbon monoxide, so don't stick your lips around a car exhaust or anything like that. The reason why is the carbon monoxide has a very high affinity for that ion, so it will stick to it and you will not be able to get rid of it. So then the ion cannot pick up any oxygen and, well, you die. Silver, so the ammoniacal silver there in Tollens reagent, so what that's useful for is just your standard test between aldehydes and ketones, so that should be fairly familiar by now. Cisplatin, so it's cisplatin what you look at as an anti-cancer drug, not the trans but the cis. The reason why, it's just sort of both these on the same side here, they effectively grab onto the DNA. So in the body it doesn't actually look like that. One of the chlorines tends to get replaced, well, the chloride ions rather, gets replaced by water. And this is how it will actually stick onto it. So remember, these are dative covalent bonds here. When one of the chloride leaves, then you've got any part of the DNA which has effectively got a lone pair of electrons. So nitrogens, oxygens, whatever about, well, they can form a dative covalent bond to the platinum there instead. And if you've got a water here, well, you should recognise this as a hydrogen bond here. So again, any nitrogens or oxygens with lone pairs of electrons, well, they can be attracted to the hydrogen here. So there are obviously some risks associated with using it, because as much as it will bind to any DNA of cancerous cells and stop them replicating, it will also do exactly the same to healthy cells. So there is a risk, obviously you could die from taking in too much of this, and obviously there will be side effects even on the small scales, how people's hair drops out, things like that. So the reason why, as I just said, it binds to healthy DNA exactly the same as it'll bind to any cancerous ones. But if you don't take it, you're in trouble in any case. And there finishes off the very long transition metal topic. Thank you.